Okay, so once you exit out of geometry, you'll see this little green check mark, and that means you are good. Now we'll come over here and double click model, and it's going to open up the GUI for hydrodynamic diffraction for aqua. And so as you can see, like I said a second ago, whenever you import it, wherever we split it, that's going to be where it pierces the surface of the water. And so this is water, this is air. And so this amount will not be treated in the hydrodynamic diffraction. So this is going to be treated as non-diffracting. And so although these elements will be meshed, they're not going to be calculated in the hydrodynamic diffraction. This warning error is just talking about hydrodynamic response, which is kind of like part 2 of aqua. So we have diffraction, which is a frequency domain analysis. Then we have hydrodynamic response, which is a time domain analysis. You can use hydrodynamic response, you can use WEXIM. I like using WEXIM for wave energy converter because it's really intuitive. The people at the WEXIM, at the WEXIM issues page and at NREL in India are super, super helpful, super nice. So I really like WEXIM, but we'll get to that later. First thing we're going to do is I like to change some of like the project settings, like the geometric features, just because eventually we're going to come over here and add a point mass. And as you can see, if I do, it just completely engulfs the flap. And so let's come over here to project, maybe change global coordinates. I don't know, just change it to some arbitrary numbers. So now it's effectively gone. Let's try maybe 7, 2. That's better. Okay, it's not great, but it's better. So we can see at this point that these indicators, like there's one for a wave direction, see how massive they are, like they're a little bit smaller and more manageable. First thing we're going to do again is we're going to change the computational domain size. And so you can make the water size in the X direction, the water size in the Y direction, whatever you want. I'll just change it to 5 for both. And then the depth of the water, let's just make it, let's see, how does that look? Let's change it. So we'll try to make this as close to the bottom as possible. One way you can do that is come over here, SolidWorks, hit this measure tool, and that point is negative 0.41. So let's try. Water depth should be 0.41 maybe. Yeah. Okay. So one thing you got to be careful of though is that the bottom of this flap is so close to the bottom of the computational domain that you might run into some errors that will say the device is too close to the seabed. So to fix that, you can just change this to point, a little bit more, and that should fix the error. If not, then we'll come back and try to fix it. But that's what we're going to be working with for now. This is essentially the sea floor. This is the air. And so once that is done, we'll come over here to flap, again, add a point mass, and that's just going to be like the where you define the center of gravity of the flap. So come over here, oh, whoops, I'm at the wrong one. Well, actually, let me walk through this first. So structure is free to move. Yes, that's going to be, you have free to move or fixed in place. If you're modeling a base, like the flap was fixed to a base, then you would change the base to be fixed in place. Now, if you're doing diffraction, aqua diffraction, you'll see in the theory manual that aqua is limited to 12,000 diffracting elements and 18,000 total elements. And I'll get to that in a second, but essentially if you have a base that you put in here and it's fixed in place, you're not going to be getting your added mass or, you're not going to be getting your added mass or your radiation damping terms. You're only going to be getting really wave excitation. And so if you're interested in that, then go ahead and model it. But for my case, inserting the base was just kind of like a waste of elements that I could use to refine my mesh. And so just use structure is free to move. The neutral axis is going to be the y-axis because that's where it's rotating around. And so sometimes you will get an error at some point. I think it's like MSME or something around there. I can't quite remember. But if you get an error like that, it could be because this is set to yes, you can change that to no, but it could be because this might be set to, X. And again, you'll get a warning right here when you change that. So make sure whatever axis it's rotating about, change it to that axis. So Y here is the neutral axis. I think that's it for this. Then we'll come over here to point mass. We're going to change the mass definition from program to controlled to manual. And so the center of gravity is what we want now. So this is the point mass. One thing that you will see in papers, let me just state this, is that you'll see sometimes they'll say the hydrodynamic coefficients, which are here, the what are they? Wave excitation, radiation damping, added mass, like all those things. Those are your hydrodynamic coefficients, and you'll see sometimes that they say they were calculated at the hinge, or they were calculated at the flap's center of gravity. If it was calculated at the flap's center of gravity, then that's going to be the center of gravity of this flap, which in our case is the center of gravity here is x0, y0, and z negative 0.13. So I'll go ahead and change that. And so you'll see that guy move. That's the center of gravity for our flap. If we wanted to calculate it about the hinge, then we would change it. We would go over here to move copy. I'm sorry, no, we wouldn't. We would come over here to measure, and then we would hit, we'd try to find a point, maybe a point right here. And so we're only interested in the z, because obviously in the x direction, this is negative 0.6. Obviously, it would be like in the middle here and in the middle in the y direction. We're just looking for this coordinate, so negative 0.35. So if I wanted it to be about the hinge, I would change it to negative 0.35. And now it's a little big, but if you shrink this down, it is directly in the center at the hinge. But again, we don't want that for this study. We're going to do center of gravity because you need the center of gravity to run this in WEXIM. You can't use the hydrodynamic coefficients from the hinge. It has to be from the center of gravity. Next thing, we'll come over here. We'll come back to this device, mass 32.42. I don't think I copied all of it. So. All right, and now radius of gyration. You're going to have to fill these in, but one thing you can do is change this from the inertia values to, you can directly input the inertia values. And so what we're going to do is we're going to come down to the inertia values. I'm going to be using these because these taken at the moments of inertia taken at the center of mass and aligned with the output coordinate system. So we're going to be using these. So 3.45, 0.79. And then LZZ is 2.74. Okay, so now the point mass is defined. For this analysis, we're not going to need any connections. You will see in some places that you can insert a joint connection and you can change it to a hinge. And so that sort of kind of works. This will work. This is more useful in hydrodynamic response. But if you're going to be using hydrodynamic response, you can specify this there in hydrodynamic response, or you'll specify this joint in WEXIM when you use it, either as a constraint or like a rotational power takeoff. In this case, it would be rotational power takeoff, and that'll essentially be the same thing as a hinge joint. But in this case, we don't want that. We're going to then move on to mesh, and I'm going to make that another video.